In this class, we have to discuss the Heisenberg's uncertainty principle. You might have heard about or you might have studied about Heisenberg's uncertainty principle. From the school level itself, we are hearing Heisenberg's uncertainty principle. Heisenberg's uncertainty principle states that for a moving subatomic particle means like electron, for example, when we take the momentum and position of such particles cannot be accurately determined simultaneously. That is what Heisenberg says. So when we talk about classical mechanics like bigger objects, we cannot compare their properties with subatomic particles if the particle size is reduced to very tiny. So here in case of electrons, it's a very tiny particle, and then its properties are totally different in that size. So that's what Heisenberg says. The true properties like the momentum because of the velocity of the particle and the position at a particular position cannot be simultaneously determined for the particle. That's what Heisenberg's statement. Okay, so this statement is only applicable to the subatomic particles or particles of very tiny size, not for bigger objects like a bed or a vehicle or something like a ball, like that. So let us discuss how and what it is. So any method for determining one of the properties, momentum and position of electrons simultaneously, would necessarily disturb the system. So if you want to try to measure simultaneously the position and momentum of electron, it will disturb the system and would make the accurate determination of the other one practically impossible. Okay, so once you try to measure the position of a moving subatomic particle, the momentum will be disturbed. So we cannot, at the same moment, we cannot determine the momentum. Or if you want to try to calculate the momentum of electron, the position will be disturbed. So we will be discussing all this, how and why it happens. And his findings has come to be known as the uncertainty principle, and this is what is called uncertainty. So there is an uncertainty in finding out the position or momentum simultaneously. Okay, so Heisenberg's uncertainty principle states that it is impossible to determine simultaneously the position, momentum or velocity, it is related to velocity of a small moving particle like an electron at a given instant with absolute certainty. It is impossible. Okay, and his equation, it's a very famous equation, delta x into delta p greater than or equal to h by 4 pi. H is Planck's constant, delta x is uncertainty in position, delta p is uncertainty in momentum, and momentum is equal to mass into velocity. Okay, so you will be knowing all these things. It can be seen from the expression that if delta x is made small, if this is made small or this is a very small quantity, then delta p will be high. Delta p increases and vice versa because this is greater than or equal to. So once one of these quantities are low, this quantity will be high. Okay, if this is low, this will be high. Uncertainty principle declares that the more precisely determined position of a moving particle, the less well to determine its momentum. Okay, so this is what the statement also says. So we can write this equation as delta x as such we have written, and then momentum mass into delta v determine the move. Okay, greater than or equal to 4 pi. We have taken to the right hand side, delta x into delta v, uncertainty in measuring the position, uncertainty in measuring the velocity of the moving subatomic particle greater than or equal to h by 4 pi m. So now we are coming to discuss how the momentum and position of a subatomic particle is measured. In order to determine the position of an electron at a given instant by the use of radiation, so normally electrons will respond with a particular wavelength of light impacts on it, falls on it. Okay, so here also we are trying to determine the position of electron at a given instant by the use of a radiation. A photon of small wavelength is used. Okay, so here we are using a radiation with a particular wavelength. So normally here for determining the position we are using very small wavelength of radiation. So if you use small wavelength of radiation, the momentum will be large, because momentum and wavelength is related by the equation P momentum is equal to h by lambda. Okay, so the lambda is low, P will be high. So wavelength is small, low, and then definitely the momentum will be high. Momentum of the radiation is high. Okay, but the impact of a highly energetic photon would result in a transfer of energy from the photon to the electron. So here what happens, electrons will respond when radiation of a particular wavelength falls on it. Okay, so here what happens is, when this photon falls on the electron, then there will be a transfer of energy from the photon to the electron is taking place, and obviously change the electron's momentum. If the energy transfer is taking place from the photon to the electron, definitely the momentum will change. So it cannot be determined simultaneously. You can determine the position, but you cannot determine momentum simultaneously, because if it gets extra momentum by colliding with the electromagnetic radiation. Okay, so this is the essence of uncertainty principle. On the other hand, if a proton of a large wavelength, so large wavelength means small momentum, is used, the impact will not alter the momentum of the electron. So here if you use a large wavelength radiation, then its momentum cannot be not much altered, but the position cannot be determined. Position cannot be determined by using radiation of large wavelength. So position can be determined by using radiation of smaller wavelength. Okay. Now we are going to give the explanation how it is applicable only for moving subatomic particles. For a moving objects of observable size like a ball, car, bird, etc., the certainties in position and momentum are insignificant because of their large masses. Because a material with very high mass, we may not bother about what is the small change in momentum or small change in the position while determining the other property. Okay, so because for example, when you go to a jewelry shop, and if you want to buy a earring or what to say, a chain or something, they will weigh the material in a high precision balance. But when you go to a grocery shop and if you want to buy 1 kilogram of sugar, they won't bother about very slight change in the weight of the material. Okay, so likewise here in subatomic particles, if there is a tiny change in momentum or tiny change in the position, it makes a huge difference in their properties and applications. That is, uncertainty principle has no meaning for the large objects that we normally see in our daily life. Okay, so uncertainty principle is applicable only to very tiny particles, not for bigger particles. However, in the case of extremely small microscopic particles, the uncertainties in position and momentum can be of significant proportions in comparison with their actual size and cannot be neglected. So for a tiny particle or subatomic particle, we cannot neglect the position momentum of the particle, because it makes huge difference in their property. So now just introducing Werner Karl Heisenberg. He is a German theoretical physicist. He was born in 1901 and died in 1976, and he got Nobel Prize in the year 1932 at the age of 31. He is the third youngest scientist who received Nobel Prize in the history of Nobel Prize, and in the history of physics. He got Nobel Prize at the age of 31, and the youngest person who ever got Nobel Prize is Malala Yousafzai. You might be knowing her. She got Nobel Prize for Peace at the age of 17. And the second person who got Nobel Prize, the youngest person who got Nobel Prize was Lawrence Bragg. You might have studied the Bragg's equation, lambda is equal to 2 d sine theta. And then the next person, youngest person, is the Heisenberg. Now let us discuss the significance of uncertainty principle. We are just discussing the significance of uncertainty principle on the basis of the existing Bohr's theory. Because as you know, Bohr's model of an atom explains the movement of electrons around a well-defined trajectory around the nucleus. Okay, so the position is fixed according to Bohr, but the momentum only need to be calculated. Okay, so there is no uncertainty in Bohr's model. But once uncertainty principle proposed by the Heisenberg, the Bohr's theory was not acceptable. Okay, so let's discuss it. The impact of the uncertainty principle on the Bohr's atomic theory is of great significance. Bohr predicted well-defined trajectories. That's what we were studied already. Trajectories or orbits, it is called orbits, for electrons to revolve around the nucleus. Since the trajectory of any revolving object is determined by its position and velocity at various moments. Okay, so there is no issue if the electron is rotating around the nucleus at a fixed distance. The position is fixed. Then there is just a need about measuring the momentum of the particle. Bohr's prediction meant that both the position and momentum of an electron in any orbit at any instant could be known with certainty. Okay, but uncertainty principle clearly says that there is an uncertainty in measuring the momentum and position of a subatomic particle. This possibility is completely ruled out by the uncertainty principle. Therefore, it is inappropriate to imagine the electron as electrons circulating the nucleus in well-defined orbits or trajectories. So this point in the Bohr's theory is not acceptable. Okay, and in general, the uncertainty principle rules out the existence of definite path or trajectories for particles at the subatomic scale. Okay, so subatomic particles are around the nucleus, available around the nucleus, but it is not on a fixed trajectory or fixed orbit. In other words, the classical picture of electrons moving in fixed Bohr orbits of fixed radius with a fixed velocity does not have any significance according to the uncertainty principle. Okay, so it is very clear. After the uncertainty principle explained the uncertainty in calculating the momentum and position of a subatomic particle, the Bohr's theory was unacceptable because the position is fixed in Bohr's concept and also the velocity is also fixed in the Bohr's concept. This means that instead of talking about the precise position and momentum of electrons, we can only talk about the probability, underline the word, probability of finding the electron at a given position with a given momentum. Okay, so now hereafter we are only going to talk about the probability of finding the electron around the nucleus. It is just a probability to find the electron. It is not exactly at the same distance. It is not exactly at the same velocity it moves. Okay, alright. So you underline the word probability of finding the electron around the nucleus. That is all about quantum mechanics. Okay. So solved problems, some simple problems are given. First one is calculate the uncertainty in momentum of a particle whose uncertainty in position is of the order of 1 Armstrong. Here you got uncertainty in position 1 Armstrong. You just need to calculate the uncertainty in the momentum. We have the equation, Heisenberg's uncertainty principle. Equation is there. Delta x into delta p equal to h by 4 pi. Delta x is 1 Armstrong given. So we have to just convert it into meter, 1 into 10 power minus 10 meter. and then max Planck's constant 6.6 into 10 power minus 34 joule second. We need to calculate uncertainty in momentum. Okay, so just to substitute the values in this equation, then we get uncertainty in the momentum equal to 5.529 into 10 power minus 25 kilogram meter per second. Second question is also a simple question. Calculate the uncertainty in position of a particle whose uncertainty in momentum is 1.65 into 10 power minus 2 kilogram meter per second. And then here we have been asked to calculate the uncertainty in momentum. So uncertainty in position, we got the value of uncertainty in momentum of the particle. Okay, just substitute the values here. We need to calculate uncertainty in position. So h by 4 pi delta p, substitute the values in the equation, then we get uncertainty in position of the particle, 3.18 into 10 power minus 33 meter. Next question is calculate the uncertainty in the velocity of an electron if the uncertainty in its position is 100 picometer. Okay, and mass of the electron. So we have been asked to calculate the uncertainty in velocity. So momentum can be written as mass into delta v, uncertainty in velocity and mass of the particle. Mass of the particle is given 9.1 into 10 power minus 31 kilogram. Okay, it can be simply substituted in the equation. Delta x is obtained 100 picometer. So picometer is 10 power minus 12 meter, and should be given the value or substitute the value here, and m mass is given, and delta v we do not know. Max Planck's constant 4 pi into, we take this value here, then we get the delta v. Okay, so delta v is equal to h divided by 4 pi into m into delta x equal to calculate the values, and then we get 5.78 into 10 power 5 meter per second. Okay. All right. So I am stopping here. We will